All right, so let's start with a little disclaimer here on distributed systems and a distributed systems career. A career in distributed systems is both exhilarating and frustrating. When things work, it's like a symphony. When they don't, it's like an 11th birthday party where half of the kids are on speed. I think this is a pretty accurate description of what happens when you venture into the space of distributed systems. And this stopped responding. So I think this is it for today. Thank you very much. So is there any way I can, let me just close and restart this. Okay, this is gonna be better. I'm gonna just mirror the screen and then we're going to be able to do something. All right. Okay, so distributed systems, a bit more on that. What happens when you get into this space is you start reading papers. Papers are recursive, which is to say when you start reading one, you find references, you read more of them, and you do all these theoretical things, and you devise proofs that prove that the system works. At the same time, you have a real system, and you try to convince that system that, in fact, it also in practice should be working, and it doesn't. And so when you do that over the years, your sanity slowly leaves you. And the reason I'm saying this here is because don't come to me in 5 years and tell me that I ruined your life and that you're now in this weird space where you can't think of anything else than all of these things. And I really like it, but it's not for everyone. So a few words about myself. My name is Manuel Bernhardt. I help companies getting started with reactive systems. Usually my clients fall into two categories: the ones that start and figure out they need help and call me, and the ones that start, do it on their own, go to production, and then they call me, and then they're kind of stressed. I'm a Lightband consulting and training partner, and I focus on Akka Cluster and Akka streams mostly. And I'm also a scuba diver, which is sort of, I live in Austria, we don't have a sea. This is not the Danube, so yeah. Let's start with a motivational quote. Life is a single-player game. You're born alone. You're going to die alone. All of your interpretations are alone. All of your memories are alone. You're gone in 3 generations, and no one cares. Before you showed up, nobody cared. It's all single-player. Very nice quote by Naval Ravikant, the CEO of AngelList. Are you motivated? I'm doing something wrong here. So I can at least use the quote to motivate this talk because it fits really well to the idea of a single node in a cluster of computers. Okay, you can really translate that well. It's all single player. We like to think of clusters as this thing where there are many computers and we all know who is there, okay? This kind of God view that everyone is there. But the reality of it is you don't write software that runs on these things, on the ether between these nodes. You run software that only runs on one machine. And when you look at the world from the perspective of this one machine, all you see is other nodes through this network. Or maybe you don't see it, you don't see one of them because maybe the network doesn't work, or maybe the node is gone, or God knows what. So this is really sort of something that I want to convey during this talk, that you have to reason in terms of one machine that's in this unknown world and looks at it. It's all single player. And so when we talk about building clusters, there's 3 things we need to do. We need to discover who is there, who is joining, who is leaving. We need means for failure detection. So who is in trouble, who is gone, who is going to come back. And then finally, when you're building a cluster, one of the reasons you want to do it, it's not the only one, but one of them is that you want to know who has availability to handle the incoming load. So you need some kind of load balancing. And it turns out that there is an abstraction that lets you do that. And that abstraction is the one of group membership. If there is a group membership service that runs on all the nodes, and every node then from the service gets to know who is there and who isn't, etc., that makes the life of building a distributed systems a lot easier. So the question then is, how do we implement such a group membership service? And for this, we need three things. Again, we need failure detection, dissemination, and consensus. So let's start with my favorite one. That would be failure detection. For this, we take Wish We're Here from 75. I don't know, I have an irrational interest in failure detector algorithms. Failure detectors have two key properties. The first one is completeness. So when a node crashes, every other node should know that this node is gone. We don't want any node to still try to talk to it. So this is completeness. And the second thing is accuracy. That is to say that the healthy nodes should not start suspecting other healthy nodes of having crashed. We don't want false positives. We want our system to be stable. And then there's other things that we have to think about in real life if we want to make this work. Pesky little concerns like speed of failure detection and network message load, because they're relevant in practice as well. Kind of makes it a bit harder to achieve this, but we need them. So in distributed systems, what we do, we can prove that things are impossible. So in one thing that's impossible, that we have proven to be impossible, is that for a failure detector algorithm, it's impossible to deterministically achieve both completeness and accuracy over an asynchronous unreliable network. So the type of networks that we have are asynchronous and unreliable, which is to say that we can't have both of these things. So we make trade-offs. What we do is we talk about strong to weak completeness, where all or some non-faulty members detect a crash, and strong to weak accuracy, where there is no or there are some false positives. And it turns out that in practice, most applications, they want strong completeness. They want everyone to know that when a node has crashed, and they trade that in for a weaker form of accuracy. It doesn't mean that the weaker form of accuracy is necessarily bad. It just means that there is going to be some false positives around. So now let me talk about a few failure detectors. First of all, the very nicely named Phi Adaptive Accrual Failure Detector. Such a nice name, comes right down your tongue. And this one has been popularized by Cassandra. What it does is it's an adaptive failure detector, which is to say it tries to adapt to changing network conditions. If things go slower or faster, it doesn't sort of just stop working, and it tries to adapt. And it introduces this notion of accrual failure detection. Because most traditional failure detectors, they tell you either the node is trusted or it's crashed. It's black or white, but you don't have anything in between. So what the accrual failure detection does, it gives you this suspicion value between these two extremes. And you can set a threshold. And the threshold is sort of, you decide what the threshold is, and then you decide what actions you want to take. So for example, here with a low threshold, you get a really fast detection time. But conversely, with a low threshold, you also get many false positives. Your mistake rate is high. So you make the decision. There's a sweet spot between 8 and 12. If you run anything on AWS, you want to go to 12 or higher. But I'm not going to continue talking about AWS and their network quality, because then I will talk about this for a long time. There is another accrual failure detector called the New Adaptive Accrual. It's not a very nice name, but the advantage of this one is that it's much simpler to implement, much simpler than to calculate phi, the suspicion value, sorry. And then it's more, so I implemented this one for Akka Cluster. I found it's more adaptive. So it's, when you run this in a cloud environment, it sort of does a little bit better than phi. But it's still the same idea, right? It's still adaptive accrual failure detection. There's nothing much new. So let's look at another one here, the swim failure detector. So the swim failure detector is really a failure detector and a good dissemination component. And the idea is to say, we have not only 10 nodes, but maybe hundreds of nodes. But we still want the same guarantees, no matter the scale. We want to scale, we want something scalable. And so the problem at scale is false positives. And so the SWIM sort of devises a few techniques to bring down the amount of false positives. So for example, when a member learns that it's suspected of having failed through gossip, it can say, hey, I'm still alive. Please don't remove me. That's one thing. The other thing that it can do is this mechanism called indirect probing. So let's say the way it works and the way the failure detector algorithm works is one node will ping another node at random, and then the ACK gets lost or it comes back too slow, for example, because it's running a JVM and the JVM was doing garbage collection and then it was not answering fast enough. But instead of just starting to suspect the node of having failed, what then happens is that this node will issue ping request messages to other random nodes, which then will go and ping that node. And then maybe one of them gets an answer, which then gets forwarded back to the initial node, who then knows, okay, this node is not gone, it's still there. Okay, we're safe. Now, the thing I wanted to say is that SWIM in practice, so in the paper it works really nicely, in practice, it kind of sinks. It doesn't really work. There's way too many false positives. So the guys at HashiCorp, you might have heard of them. They do things like Console, Vault, Terraform, etc. So they do many cluster-related things. They implemented SWIM. And SWIM is what you see at L0 here. Up here, the first row, you see that the number of false positives events is quite high. And so what they devised is extensions to SWIM, which they called Lifeguard, appropriately so, and they got down to less than 2% when you apply all of the extensions, less than 2% of the false positives, which is really great. I think it's open source. It's called memberlist. The implementation of the basis. It's written in Go, and I think this is state of the art. I haven't found anything that's sort of better at the moment in terms of like false positives and failure detection. All right, so let's continue now. And what I want to talk about now is the second thing you need to do when you want to build a cluster, and that's the process of disseminating things. So here I'm choosing Pulse from 95, and you will see right now why I chose this album with the Pulse, this pulsation thing. What do we need to do? Well, we need to propagate things in a cluster. So in this small cluster, you think, okay, one node can talk to every other node, but that doesn't scale, obviously. You need some other way of disseminating information about members joining, leaving, members failing, etc. All of this data that you want to carry out in the cluster. So then naturally, what you want to do is say, hey, multicast, let's do that. But what happens is when you go to your sysadmin and you say, hey, can I have multicast? They will, turn around and walk away, and that's pretty much because currently I don't know why really, but it seems that the state of multicast, be it hardware multicast, IP multicast, or UDP multicast, the state is not really great. And in sort of every client I've had, when multicast says, oh no, we can't do that in our data centers. It's like I've had one client, they had a really strong political tie to Vertex, but they went for Akka because the Vertex cluster back then only had multicast discovery. So this is like a really strong thing. So what do we do? Well, we go back to the good old days of peer-to-peer networks. Anyone remembers Napster? Yeah, Kazaa, okay. Downloading MP3s in all legality. And so what happened back then is, this peer-to-peer networks, what you do, you have the same problem. You can't just talk to everyone. And you don't have a multicast either. So what you do is you devise algorithms to spread information faster out in such a network. And that's where a lot of great research has been done, protocols like CORD for search, things like that. What came out of that is different gossip styles. And by far the most popular one is the random gossip. So that's what you see in this little animation. Every tick of the clock, you will see one value being spread out. Every node spreads out the word at every tick of the clock, and this propagates really fast. So there's been more research done on this to be more deterministic, for example, like round robin or binary round robin gossip, but this sort of didn't catch on. People always sort of revert to random gossip. There's another approach that SWIM is taking, which is to piggyback on another protocol. So in SWIM, you have a failure detection protocol that sort of does this ping, ACK, ping, rec messages, and the gossip is piggybacked on these messages. So whenever someone does a ping, they also include a little bit of gossip in the ping. So this is called infection-style gossip. Outside of SWIM, I haven't really seen it. There is many ways to optimize gossip, but this has been optimized that way now due to lack of time. I'm happy to talk about this after, in a break or so. And now, for the third part, which I think is probably the hardest part in distributed systems, and makes you go crazy. This is why I picked a momentary lapse of reason here, is the problem of consensus. How do we make it so that all the nodes in our cluster have the same idea of who else is there? You know, how do we agree on this? And it turns out that this is hard. Let's start again with an impossibility result here. The one of group membership, which is kind of unfortunate because that's what we're trying to do here. So group membership with a single group, okay? We want a single group. We don't want many groups. We want a single group. Is impossible when there are nodes that are suspected of having failed. Okay, the moment that I have one node that is sort of suspected of having failed, even when I say, okay, I'm just going to remove it, ignore it, that doesn't work. It's been proven to be impossible. You can't have primary partition membership when there is one node suspected of having failed. Yeah, so that means that, again, we're kind of in an odd place. What it means is we should not be making membership decision when there is one node or more than one node that have suspected of having crashed. We can't do anything. We can't let new nodes in. We can't let nodes out. We shouldn't be doing anything so long as we haven't resolved this thing, so long as we haven't sort of decided to kind of ban the node that is suspected, and so long as we don't have this convergence of the cluster state again. And that is sort of an important point here, because otherwise you end up with this sort of a scenario where your membership doesn't make sense anymore. So how do we do this? Well, there's a few things we need to do. We need to first reach consensus on one of the things we always need to reach consensus on is time. And so if you walk out of this talk, the one paper I would like, because there's many of them, but one paper I would really recommend you to sort of look at is this one. It's Leslie Lamport's Time, Clocks, and the Ordering of Events in a Distributed System. It's because this paper won a Turing Award, and it is probably it is actually the most cited paper in distributed systems research, or even in computer science in general. I forgot which one of the two. It's really well known, and it has many, many great ideas in it. So you have to read many times to sort of grasp all of the ideas that are in this paper. And the question is here, I have many machines. How do I establish an order of events happening in these different machines? That's where we have this notion of logical time that comes in. And Lamport clocks give you this ability of saying this happened before or this happened after. But it doesn't tell you this happened at the same time, and oh, by the way, it's the same thing, or oh, by the way, no, it's not the same thing, it's conflicting. It doesn't give you that. In order to detect conflicts, what you need are vector clocks. So vector clocks are vectors of Lamport clocks that have the size of the members, and every member for every event gets a version that sort of when you combine them together, you can then detect conflicts and figure out that you need to merge things. Now, in parallel to Lamport clocks and vector clocks, another tool has been developed that's very similar and oftentimes confused. It's the one of version vectors. And then the evolution of that dotted version vectors, which sort of fixes some of the false positives in there. But version vectors they're really almost the same, but they're not the same. There's a blog post you can read. Version vectors are not vector clocks. Version vectors are about replicas, okay? They're about detecting conflicts in replicas. And it's not the same thing as ordering events. There's two different things, and one is unbounded, the other one is bounded. So just to mention them, don't confuse them. Yeah. So just to tell you that, and because I need one slide with code at least, just to tell you that this is not something I'm just citing here out of academical reasons. This is actually used in real life. So this is Akka Cluster's gossip message, and you can see it has this version, and the version is a vector clock. And what happens in Akka Cluster, the nodes exchange gossips, and so using that version clock, they can figure out is this gossip older, newer, Is it the same, or are they conflicting, and do we need to merge? This is done using vector clocks. Another very important thing when you want to sort of reach consensus on a value, sort of agree on what the value is. So for example, here we have, let's say we have a client, they want to store a very important sequence of events. What they do, what happens, you send these events to one of the server nodes, which then replicates the events to the other nodes. And the way this is made fault-tolerant is that every server will apply the events in the same order, using vector clocks, for example, to keep the order, to a state machine. At the end of the day, when everybody has applied these events to the state machine, all the state machines will have the same value. So it's a quite simple idea, really. Also comes from that 78 paper by Lampert. It turns out it's surprisingly complex to get this done in real life, because in order to implement this in real life, what you need is a consensus protocol. You know, you might have heard of Paxos, Raft. You probably haven't heard of CAS-Paxos. Anyone heard of CAS? Yes? Okay. Yes, another geek with me here. This is like 2 months old CAS-Paxos. And it's great because it makes do with the log, which is awesome. So the way a consensus protocols works, usually, except CAS-Paxos, you have this log, and then you commit at a certain point. You need leaders, you have a leader election. So Paxos was hard. There was first the Paxos, the part-time parliament. Then there was Paxos Made Simple in 2001. And then, 13 years later, where RAF came out, and the paper is called In Search of an Understandable Consensus Algorithm. Just to tell you that this is, even for our hardcore distributed systems people, this is hard stuff. This is difficult. Now something more hip and more modern, CRDTs. Or conflict-free replicated data types. Just saying that makes you sound cool, even when you don't know what it is. So the idea is to say, okay, let's just not have conflicts. It doesn't matter if I have a network partition, if my nodes can't communicate and synchronize anymore. When they can talk again, if I use these conflict-free replicated data types, I can always merge. And there's two families. There's ones that rely on the commutativity of operations. 1 + 2 = 2 + 1. In practice, that also means that you can't afford to lose messages, because if an operation is lost, then it doesn't matter if it's commutative or not, you're losing your data, your value here. And then there's the ones that are based on the conversion of state, and they use monotonic merge functions. Monotonic means that it goes in one direction only, either up or down. In this example, what we have 3 nodes. They start with 3 different values, 1, 4, and 0. And as the events propagate, at the end of the day, everybody has 4, because the merge function is max. So we always take the maximum. At the end of the day, we're going to converge to 4 everywhere. So this is pretty powerful, and it is called accurately so strong eventual consistency, because there's a rather strong guarantee that we will converge when the partition is resolved or when the nodes can talk again. A lot of active research in that space. And then my favorite, finally, is reaching consensus through conventions without communicating. This is awesome. You reach consensus, you didn't even talk to one another. You don't need a network. So for example, Akka Cluster doesn't have leader election, it has leader designation. So what Akka Cluster does is, it has a list of members that's propagated through gossip. It orders them by IP address. It puts the one that are not fit to be leaders at the very end, and it takes the first one. Every node does that independently of one another. They all end up with the same result. And that's how Akka Cluster designs a leader. And every time there is a change in membership, or depending on which node goes away, you may see the leader jump from one node to another. Okay, I have surprisingly much time left, so I may even be able to catch up some of the time So one example here is Akka Cluster. I didn't want to go into Cassandra and something. Also, I think I did say that I was going to talk about Akka Cluster. So Akka Cluster uses the phi adaptive accrual failure detector with modification for the JVM, which takes into account the fact that the JVM has garbage collection, and sometimes it just freezes dead. And then it's alive again, but the others think it's gone. It uses the strategy, it uses ping pong, so it doesn't use simply heartbeats, it uses ping pong requests, so one node is gonna be monitoring 5 other nodes, and it's gonna measure the round trip time, feed that to the Accrual failure detector, which then sort of gives back the suspicion value, which you then set in the configuration to say, okay, we're going through to another state now, it's suspected of having failed or not. In terms of dissemination, it uses random gossip with a twist. And the twist is that in the gossip message, Akka Cluster keeps a track of who has seen a certain version of the gossip. And that way, it can gossip to the nodes that have a higher probability of not having yet seen that gossip message. Okay, and that way we converge faster. In terms of consensus, the leader is designed by convention, and then it's the leader that makes these membership decisions. I don't know if you remember what I said in the beginning of the consensus, where I said you don't make decisions when there is nodes having suspected of having failed. Well, this is the leader that ensures this. The leader sort of says, hey, no new nodes come in, nobody leaves. We first need to fix this. In terms of architecture, there is like the membership layer at the very bottom, and that's what's actually called Akka Cluster is this membership layer. Then we have a few extensions, distributed data. These are CRDTs, mostly CVRDTs at the moment. There is a cluster singleton, which, yeah, well, basically lets you deploy one thing in the whole cluster. And then on top of that, there's sharding, which lets you shard in large amounts of data across different nodes. And then at the top, that's where you build your application. You definitely don't want to use in your application what's below there, which is remoting, Akka remoting. Don't use that directly. It's only a world of pain. Use cluster. It does all of the stuff that I just talked about. You don't want to implement that on your own. So how does it work? Well, for a node, the node will join. Then it will be joining, then the leader will decide, okay, you're up now, you're part of the family, welcome. And then if everything goes according to plan, it's gonna leave, and it's leaving. Then the leader again sort of says, yes, you can leave now, then it's exiting, and then it's removed. And yeah, that's pretty much the thing, that's how we would like things to work. In reality, it's not like this. In reality, what happens, the node joins, it's up, and then it fails. So it's in this pseudo state called unreachable, because the failure detector figured out it's gone. Then it's down, and then it's removed. And the thing is, a question really is what happens here? Because as you see, there is no failure detector here, and there is no leader involved. So who makes the decision? And this is a very interesting class of algorithms which are called split brain resolution algorithms. And we're out of time. So no split brain resolver algorithms for today, but I encourage you to check my blog from time to time. I intend to write about these. And these are the papers that have been mistreated during the creation of this talk. And that's all. I think there is not much time for questions, but I'm around, so thank you very much.